Hello, welcome back. So, yeah, time to do some more logistic plotting stuff. Let's go to my iPad to explain my upcoming idea. Okay, before I explain my idea, let me just review what logistic regression is doing. So we've got a bunch of data points here at the 0, some here at 1, and then we are fitting a curve that looks like that. And so that equation is the probability of y equals 1 is equal to e to the b0 plus b1x, if there's only one variable, divided by 1 plus e to the b0 plus b1x. I think that's what it is. Not entirely sure, but that's okay. And so what you can do then is you can solve for these parameters here. And so what that ends up giving you is that the log of p divided by 1 minus p is equal to b0 plus b1 x1, or x or whatever we had it as before. So this is called the logit. And what we can do is, instead of expressing the curve on the logit scale, we can instead express the relationship between x and y on a log odd scale. And so what that ends up looking like is more like this. So you still got the x-axis right here, but now we've got log of p divided by 1 minus p. And so it's pretty easy to translate between those two things, which is great. So why am I talking about this? The reason why is because the next things that I'm going to do, I feel like, and I don't even know why I feel like this, but I feel like we need to convert it to a log of the odd scale. Maybe I can explain why I'm thinking of that, and you can discover in real time with me. Because what we're doing is we are binning the different x values and coming up with a proportion over here versus here. No. I'm just realizing that these, actually let me draw those in a different color. These big dots are not going to line up with whatever the little dots are. I'm just drawing fake dots around that. But anyway, so you got something that looks like this. And so that's what we did last time. And by doing that, we were able to introduce kind of like a scatter plot for the logistic regression. And so what I want to know is what happens first when I convert that to the log odd scale. I'm guessing it's going to look, that same plot is going to look something like this. So why am I doing that? I'm doing that for two reasons. I'm going to extend this because just like in regression, it's great to have a scatter plot, but it's also nice to have other things, like particularly two things that I'm trying to add to this is diagnostic plots, like a residual dependence plot, specifically, as well as an added variable plot, because I use those two types of plots all the time, and it would be nice to see if they work the same way with logistic regression that they work with regular regression, at least in the way that I've conceptualized it. So I think that's what I'm going to do. And now the question is, why do I feel the need to do that? So the idea is, I think, if you keep this on the probability scale and you do a residual dependence plot, I don't know how these residuals are going to behave. And I think it might be cognitively misleading what happens, because you're going to have, okay, so if I'm translating from here to there, your first data point is going to be above, your second data point is going to be below, and I'm just basically looking, oh, that's above, that's below, that's above, that's below, above, below. Hey, look at that. That wasn't intentional, but anyway, you get something like that. But I'm actually going to introduce a pattern, because one thing that we do with these is we want to see if there's nonlinearity present. So maybe the pattern of the residuals looks something like this, where there's nonlinearity. And so the residual dependence plot in a regular regression would show you if there's a pattern on nonlinearity that you haven't picked up. I'm not sure if it would behave the same way, and what does that even mean, because this scale is now on a probability scale, and we know that the logistic function is going to look like this, and I don't think that a missing nonlinear pattern would look the same, and I don't know how it would look. And maybe what it would look like on a residual dependence plot is it might look something like this, showing you that you have missed a ogive curve. But I don't know what is going to happen. I don't know what's going to happen if you've missed a nonlinear term. But what I suspect is going to happen is if we keep it on the log odds scale, that its residual dependence plot is going to look more traditional, more like what we would expect it to look like. That there will be a pattern like that where there's this nonlinear effect. That's my intuition, but that's something that we can explore. So I'm going to step into R and try to see what it would take to convert what I already have into a logit scale. So that was a couple days ago. So now I am actually ready to step into R because it took me some time to work out some bugs and stuff. So now we're going to explore in R. And by the way, this is like the third time I've recorded this video because I either have to pause the video because I need to debug some R code, or like the last time I recorded my screen, but for some reason my screen was cropped. Somehow it had gotten zoomed in. I'm going to try to make sure that doesn't happen this time. All right, now we've got my desktop and you can see the whole thing. Okay, so I decided to put all this stuff into FlexPlot and I'm going to require the tidyverse. So I decided to create a simple function that takes 3 arguments. This is the betas and it's a vector. First argument is the intercept of the betas. Second argument is the slope of x1. Third argument is the slope of x2. Fourth argument is the interaction between x1 and x2. And then core is how correlated the predictors are. And then n equals 500, but you could put whatever you want. That's just the default that it does. And I'm actually going to start by doing a lot more than that, just because I want to see, I want to get rid of sampling variability, if that makes sense. Because this is all random data. And so even though I'm asking it to give me these parameters, it's not actually going to be exactly that. And I'll show you what I mean. Oops, got to read in the function first. So if I go summary glm y tilde x1 plus x2 data equals d, family equals binomial, then if I look over on the right side of my screen, I see the intercept. Even though I have 10,000 participants, simulated participants, a sample size of 10,000, the intercept isn't precisely 1. The first slope is not precisely 0.5, and the second slope is not precisely 1.5, but it's pretty close, I guess. That's actually surprised me as I played with this simulate logistic function. I didn't realize how massive your sample size has to be for those to converge on the right value. So if I do 100,000 observations, that's a big sample size. And if I do that, we're still not quite there, really close, but anyway. So I'm just trying to see how well these plots work. In order to see how well these plots work, I'm going to use a very common statistical research trick where I simulate the data to have known properties. In this case, a specific correlation between my predictor variables and specific beta values. And I'm going to introduce some problems, and I'm going to see if my plots pick up on those problems. So, let's see how this goes. All right, so the first function you saw last week, I think I called it overlay logistic, a logistic overlay plot, which I don't like that name. Somebody in the comments last time said, hey, you should come up with a cool name for it, and I totally agree. I don't know what to call it though. I just don't want to use my name or my channel's name because I like my plots to be descriptive. Like I created a plot once called a hopper plot. Why? Because it looked like a hopper. And I like it when the name of the plot communicates something. Like bee swarm plots. I didn't come up with that name, but it works because it looks like a bee swarm. So I'm going to go y tilde x1 plus x2 data equals d. Okay, and I also want to increase the number of bins. So I'll go comma n underscore bins equals, we've got a large sample size. We have 10,000 participants, so why not do 1,000 bins? We can afford it. And that's what we get. And you know what? I don't want them to be separate colors. I'm going to put them in separate panels, although actually it probably doesn't matter. So what are we seeing here? We are seeing the relationship between x1 and y, and x1 has a slope of 0.5, and we are conditioning on x2, which is the stronger of the two. So actually, I'm saying when the interest variable has a strong relationship, I should put x2 first. And because we were, in this case, I'm simulating a situation where we're really interested in that x2 variable. And we get a much steeper slope, which is what we would expect. Cool. So now I'm going to use a new function that I created called Logistic Residual Plots, and I'll actually show you what would happen. So I'm going to borrow this line of code again. Oops. So I'm going to go mod equals, so I'm fitting a model first, and if I go visualize mod, then I get a plot, or a series of plots. One is my logistic overlay plot over here, and then I also get a distribution of the residuals, and then we now get this residual dependence plot analog with the bind method, and then a scale location plot. So if you have been using FlexPlot, you will recognize a lot of these plots because we use those all the time for standard linear regression. But I don't want to look at all those. I want to look at just the residual dependence plot, for now, at least. Oh, you know what? Before I do that, I'm going to look at the logistic overlay and look at it on the logit scale. So I'm going to go scale equals logit, and we'll see what that looks like. And remember, like I said, we expect it to be a linear relationship now, and so that's what's happening. Also notice that you've got this like clustering going on, that you got a bunch of values near the top, and that's because like probabilities are bounded between 0 and 1. And so there's a certain region that you just can't get beyond. You can't get a higher probability than a 1. And so that sort of clustering is common, especially if, and let me look at the original plot. The logistic overlay plot. Oh, not that one. Especially if you have a bunch of scores that are near 1, which is exactly what we have here. So there's a lot of subdivisions within x2 where the proportion of people who are a 1 are 100%. And so that's why you see a bunch of those dots right there and there and there. So that is working okay. So now we're going to go ahead and fit the model, and then I'm not going to visualize the whole thing. It's kind of lame how I have to do this. Eventually this is going to be changed. I'd like to look at just the residual dependence plot, and that's the way to do it. Data equals D. There we go. And I'm going to increase the number of bins. So n underscore bins equals 1,000. And so these are on the logit scale, by the way. If you can't tell by the y-axis saying logit scale. And what are we seeing? So remember, what are we looking for? So if this is a residual dependence plot, we are plotting the fitted values on the x-axis, which in our case, they're all going to be fitted probabilities. So that logistic curve that looks like that, those are the fitted values, and we are plotting those against the residual. So if you can imagine the logistic plot and the dots above them, it's basically like flattening out that plot and maintaining the distance of those individual data points from that fitted curve and flattening it out. That's essentially what a residual dependence plot does. But in this case, we're doing it with logistic regression, where those dots are based on the bins. What we would want to see is we want to see a flat slope, and that's kind of what we're seeing here. It does kind of peak up at the end, but maybe that's noise, but maybe it's not, though, because we do have a sample size of 10,000, and we have a bin size of 1,000. So what is that saying? That is saying that as you get closer to a 1 probability, your residuals tend to get higher. Actually, I guess we kind of saw that if we go back to this plot, that the closer you are to 1, we get a bunch of these, like where 100% of the people are getting a 1. And there, and there. I guess the fact that we see that, I mean, it makes sense that we are seeing that. But that could be troubling because and it could not be troubling. I don't know. Because the problem is, like, I know what the answer is because I simulated the answer to be something specific, and we fit the model with the correct model. So it should be flat. But at the same time, it's not, and I know why it is. And I don't know if that concerns me. Anyway, something to keep in the back of my mind. All right, now I'm going to do a logistic added plot. And if we're trying to look at the relationship between x2 and y controlling for x1, then we're going to go y tilde x1 plus x2. The variable that you put second is going to be the one that ends up on the x-axis. If you need a review of how to use the added variable plot function in R in FlexPlot, then I'll leave a link in the description to do that. I'm going to go n underscore bins equals 10,000, and it looks like this has a scale argument too. So we'll look at both of them. Scale equals probability, and I'm just going to duplicate that line and then do logit, and then we'll look at those one at a time. So, and that is cool. Okay. 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 Okay, remember each of these dots represent the residual after we fit a model. So again, this is fitting a model between x1 and y, computing those binned residuals, and then now we're plotting those binned residuals on the y-axis, and we still see this curvilinear S-shaped, what's another word for that? S-shape or ogive shape or sigmoidal shape. I don't know why it has so many names, but anyway, that shape right there, we still see that shape, and I suspect when I plot on the logit scale, it's going to flatten out. So that's my prediction. But this is exactly what I want to see. So it tells us that there's still a relationship between x2 and y even after we've subtracted out x1, which there should be, because that's how we simulated the data. And by the way, this 1.5 is going to tell R what the net effect of x2 is on y after subtracting out x1. That's just mathematically how it works. So that's cool. Now let's look on the logit scale again. I think this is going to be I think this is going to look just like a regular scatter plot. And it does, except it has a very tight curve, or very tight residuals, and it does kind of fan out at the end, so it looks like we would call that heteroskedasticity. Maybe there's some heteroskedasticity there, which there shouldn't be. But for the most part, this is behaving as I think it should. Okay, so I'm feeling optimistic so far. Under a known condition where the variable that we're interested in, x2, has a strong relationship with y, the plots are behaving exactly as I think they should. Now, one thing that just occurred to me is I think I'm going to add my predictions right before I actually do the plot.
Hi, I'm going to record this video because my dad is in his room crying right now. And
No! 5 times! Why 5 times? I can't get it right 5 times!
but he's over there, so I'm gonna record this video. So he's gonna be a minute. So for now I'm gonna be recording. So yeah, so how you liking those logistic regression plots? Okay, sounds like he stopped crying. Okay, I'm gonna let him record now. Don't forget to take a simplistics class. I think he could use the morale boost. Bye!
Well, that was unfortunate. And the other thing is that you saw my live reactions. This time you don't get to see my live reactions. Instead, I'm just going to go through what I did before. Hopefully you still like it. All right, let's step into R. So last I left off, we looked when the interest variable has a strong relationship. And now I'm going to look at when the interest variable has a very weak relationship. So x2 is going to stay our interest variable. So it has a 0.07 slope. So now if I run that, we got our data. And if I do a logistic overlay, that's happening as we would expect it to happen. That they should be relatively weak slopes. And I thought it would be a cool idea to add the logit, but also add, so this right here, this 0.07 is on the logit scale. And so with the logit plot, if I add an AB line that is equal to the slope, then it can it allows me to evaluate how close that line mimics what I would expect to see. And the cool thing is, it works. You know, there's slight deviations from being parallel, but for the most part, I expected a slope of 0.07, and I got a slope of 0.07. That's kind of amazing. That's pretty shocking. That's pretty cool. Yay! Now let's go ahead and look at the residual plots. I predicted this would be flat, and what ends up happening... Actually, this is new. Last time I recorded the video, the residual plots were behaving very weird. So, count my blessings, I guess, that I get to record this again. Anyway, this is what we see with the residual plots. Relatively flat line, which is exactly what we would expect. It does have that little curve at the end, but nothing that I'm worried too much about. And actually, I'm going to do a smaller sample size because I suspect that that sort of bend at the end isn't going to happen as much, and I guess it still does. All right, and with the added variable plot, and for these, we're looking at the relationship between x2 and y after controlling for x1, and that's the code that you would do that. I'm going to move the bins down to 500, and I will tell you why toward the end. And so, again, this is I'm predicting a very weak slope, and sure enough, we see a very weak slope. And I'm going to do the same thing I did with the logistic overlay. I'm going to add a slope to show what I expect it to be, and lo and behold, it's very, very close to what that line is saying. Actually, can I go method equals LM? Hey, I can. That's pretty good. Those slopes are bang on, man. So it's working. It is working, and I am just excited about that. Okay, so now let's look at a situation when the variables are highly correlated. And so I just gave them both, so a slope of 0.75 for x1, a slope of 0.25, no interaction, but now they are correlated at 0.5. And so my prediction, and I don't even remember how these came out, so I guess you're still getting a live reaction from me. So we're looking at a logistic overlay. This is going to be on the probability scale. This is looking at x2 given x1. So we should see a strong slope for x1, moderate for x2. But we're really only looking at x2 here. And we do get a strong slope. So that's behaving exactly as we think, except it's kind of weird that you've got this weird scattering of dots. And that's a little unusual. I would expect them to be maybe a little closer to the line, but I guess not. And now let's look at the logit scale. And those look a little less weird, so that's good. And again, I'm overlaying the slope, and it does pretty good. It's closest in the middle, which is kind of what I would expect because scores near the mean are more stable. And their standard errors are tighter in the middle. So I would expect that to happen when you're conditioning on x1 and you're looking at the panel for x1 in the middle. I would expect that sort of thing to happen. And then the other ones aren't too far off from the estimated, or what the slope should be. So I'm not worried about that small deviation from it. And again, looking at these, again, I should have put that earlier, but whatever. So now my prediction, and this is actually the first time I've looked at the residual plots because they weren't working last time I recorded. But let's see what they look like now. Okay, they're flat, and they should be flat because we have modeled everything. So that's good. Yay. Now I'm going to do a moderate, so I'm predicting a moderate slope for the added variable plots. So I am subtracting out the effect of x1 and looking at the x2 relationship. And moderate slope. Now this is on the probability scale, so we see that sigmoidal shape going on. Now what happens when I do a logit scale? And this is when I discovered something that is problematic, and I still don't have a solution for it. So I expect this slope to be 0.25. But then when I do the added variable plot, I get something very different. And that really puzzled me. And it still kind of puzzles me. Ish. So the model predicts it's going to be a positive slope, but the added variable plot shows a negative slope. Why is that? I don't know. And around this time, I thought it was weird that I don't remember why I changed the bins, but I changed the bins, and interestingly, if I change the bins to a lower number, it looks great. And then if I do even lower, actually, I don't know that that's a consistent pattern. Let's see. What would happen if I did it again? Okay. What? That's depressing. The bin size is affecting things. So yeah, just to step back and talk big picture at this point. I went into this by trying to create a scatter plot for a logistic regression, and to do that, I created these bins. And I really, really hoped that substituting data points for bins would work. And it mostly works, but it is sensitive to the number of bins. And I'm not entirely sure why. Well, I do think I have a suspicion of why. So if I have, let's see, that's 10,000 data points, and I have 5,000 bins. So these bins are based on an average of 2 data points. And so again, we're creating bins and then averaging and then computing the proportion that get 1 versus 0 within those bins, and we are creating 5,000 bins for a sample size of 10,000. So on average, there's only 2 data points to estimate that. And so I would expect instability. And yeah, I would expect instability. And let's see what happens if I run this again. I'm just going to move this down here. Okay, now I definitely am in exploration mode because I didn't do this before. If I do it again, is it going to consistently be overestimating? So I'm just going to run it a couple times. Okay, it's consistently reversing the relationship. Okay, so my first thought was that it was sampling variability because you only have 2 data points. And so that's going to be highly variable, but it's consistent. But still, you only have 2 data points. So, but if we were to do the same thing with 1,000 and do that over and over again, we are consistently about at the right slope. I mean, that's good to know that there are bin sizes that are really bad. You don't want 5,000. And there are, I'm sure you can go too low. I'm not entirely sure why, other than I know you're only averaging just a couple of data points, and that can lead to instability. I don't specifically know why it is so biased. If you have a good idea why it's biased, then absolutely let me know. But that's interesting. Okay, so, and I think this is overstating it. It's not really that depressing because it does consistently work when my bin size isn't ridiculous. So if I have a ridiculous bin size, then yes, it's not going to work very well. Okay, so now I want to investigate what happens when there's a missing nonlinear effect. And so I created a new function called simulate logit2, where instead of controlling the interaction effect, which I realized I haven't done that. I think that's right after this. But instead of that 4th slope controlling the interaction effect, it's instead controlling a polynomial. I guess I'll go ahead and show that to you real quick. So it's going to be beta 4 times x2 times x2, which is the same thing as beta 4 times x squared. So that is now controlling the degree of nonlinearity. So if I simulate that data set, and what is my prediction? It's going to be bad. I didn't specify what it was, probably because I didn't know. So it's going to have a nonlinear effect, but when you panel on the x's, I'm not exactly sure what's going to happen. Okay, that's what happens. You got this weird kind of, I don't know, it looks like, what does that look like? It looks like water from a bucket falling or something like that, that you got this kind of trail going on. So it's this weird look. And if we plot it on the logit scale and overlay what the slope should be, it's somewhat close. It's not terribly far off. And we still get that. And actually, now it looks like a heart. Isn't that cute? It looks like a heart. And at this point, I actually don't mind that the plot looks weird, because I want the plot to look weird if something weird is going on. which something weird is going on. We got this nonlinear effect of x2 on x1. So now I'm going to fit a model where I just totally miss that entirely. So I don't model that nonlinear effect. And then now I'm going to look at the residual dependence plots, and I'm going to hope. So normally if you do a regular regression and you missed a nonlinear effect, it would show up in the residual plots or the residual dependence plots. I don't know if it's going to happen here. Let's see. No. Okay. Darn. I was really hoping it would show this drastic nonlinear effect. And that's actually a really large nonlinear effect, and it's not showing up. And I don't know why it's not showing up. So that's one of the questions I have. Why is a missing nonlinear effect not showing up? Okay. I don't know. But let's go ahead and look at a logistic added variable plot. So this is going to show the net effect of x2 on y after subtracting out the effect of x1. And that works. Okay. That's cool. So the added variable plot does tell us what's going on. It tells us that we're missing a nonlinear effect. I don't know why the residual dependence plots don't, but that's okay. An area for further research. So that's on the probability scale. Let's look at it at the logit scale and see what the slope says. Although the slope shouldn't be trusted at this point because we haven't even modeled the correct effect. So that's actually really good news for our plots. We modeled a very strong nonlinear effect and chose not to fit a model with that nonlinear effect. And it does seem to affect the plots, except for the residual dependence plots. For some reason, nothing happens with those, and I don't know why. All right, and then the final condition that I simulated is when there's a missing interaction. So now that 0.5, instead of controlling the polynomial, it's controlling the interaction effect. So we have a pretty strong interaction effect between x1 and x2. And if we look at the logistic overlay, we see non-parallel lines, which was my prediction. And that's how you identify visually if you have an interaction effect, is if you have non-parallel lines. And so for low values of x1, it's a negative slope. For medium, it's positive, and it's even more positive for high values. So that's great. It's picking it up. And of course, I don't think this is going to work. Yeah, I mean, it's going to be biased. So I'm overlaying the slope of 0.25, which in the middle it is, which is actually what I would expect on average. That's what happens, which you can think of a coefficient like that as suggesting what is the effect of this variable on y when the other variable is held constant, which is similar to saying when it's at its average. So that is what I would expect within that plot. Everything here is what I expect. So that's fantastic. Now if we look on the logit scale, yeah, similar idea. And then, yeah, I didn't have a prediction here because before the logistic residual plots were showing something really weird. Now they're just showing nothing consistently. And still they're showing nothing. I mean, we see some slight bumps, but yeah, it looks like these logistic residual dependence plots are not telling us anything, which is unfortunate. All right, but now if we look at the added variable plot, and my prediction was that there would show a nonlinear effect, similar to what we saw over here. And the reason why is because the only difference between the simulate logit and simulate logit 2 is in simulate logit, that last parameter is multiplying x1 by x2, and the other one is multiplying x2 by itself. So in either case, you're multiplying things together. And so I would expect non-parallel lines to show up here, but let's see what happens. Yeah, that's what happens. And so if we look at the added variable plot, which, okay, that was unexpected. I expected to show a nonlinear effect, and it doesn't. And actually, that shows that there's nothing wrong with the model. Maybe there's a slight curvilinearity, but So that shows that these are problematic in this scenario, but I'm actually not bothered by that. because you would get the same problem with linear regression. If you jump to an added variable plot when there was an interaction in there, it would be very misleading, and you should never do that. That's why I always start with a scatter plot, where you're looking at both variables simultaneously, which is what we do with logistic overlay. So as long as you do this first, and notice, hey, there's an interaction going on, and if there is an interaction, you don't do added variable plots. So even though these are misleading, I'm okay with it, because if we followed my traditional rules of plotting, you would never look at this plot anyway in this situation. Okay, I really hope that is the last time that I have to record that video. So just to summarize what's going on here. So in the last video, I created a scatter plot equivalent for logistic regression. And this video showed that for the most part, everything seems to be working really well, except we see two problems. One problem is that it's sensitive to bin size. And if you have too many bins, then it really biases things, and that's very problematic. At least for, oh, I don't remember what plot that was. I think it was a added variable plot. It was really problematic. Might be problematic for the other ones too. So there's certainly like an optimal bin area, and maybe there's a better way to do bins. I don't know. I'm gonna have to look at that. And then the other thing is that the residual dependence plot is telling us nothing. It doesn't matter like whether we have a good model or a bad model, it basically shows the same thing, which it shouldn't do that. So that's something that's worthy of further exploration. But I am done recording. Definitely done recording. So yeah, take a simplistics class. Ease my troubled soul by giving me your money and buying a course. I don't have any live courses in July because I'm taking a vacation, but in August, I'll have some classes. I'm not sure what I'll do, but be sure to stay tuned and I'll let you know. All right, hope you've enjoyed that. I have not. All right, peace out.